Today we're going to talk about how to find areas of regions between a curve and the y-axis, and also just finding the area between two different functions, uh, but doing it in terms of y instead of in terms of x like we did last time. So the first one we're going to look at here is the area of the region between the y-axis and x equals 2y squared plus 2. And we're going to go from y equals -1 to y equals +1. So 2y squared plus 2, x equals 2y squared plus 2, is just a parabola that opens to the right. It's been shifted to the right 2 units. So it looks basically like this. So this is x equals 2y squared plus 2. And if we're looking to integrate this from -1 to 1, and the area between the curve and the y-axis, this is the region we're looking for. And so really we just need to think about this in terms of the little rectangles that we would normally draw. Like normally when we do an area under a curve, right, we think about it as a bunch of little infinitesimally thin rectangles underneath that curve that we're summing together. Well, we're going to do the exact same thing, except we're going to do it in the y direction, which means that each of these rectangles has a thickness of dy, and it has a width here going across of whatever the x value of our function is, but it's the x value of our function in terms of y, because we have to do the integration in terms of y, because the thickness of each of these little infinitely thin rectangles is dy. They're infinitely small in the y direction. So really, all we got to do here is just an integral from -1 to 1 of 2y squared plus 2 dy. And so we'll just integrate that to get 2/3 y cubed plus 2y from -1 to 1. And when we plug that in, we end up with 2/3 plus 2 minus -2/3 minus 2. And that just ends up being 4 plus 4/3. And 4 plus 4/3 is 16/3. So pretty straightforward to find the area between a curve and the y-axis. No real difference between doing it in terms of x. Just kind of think about it as if we've turned this thing on its side. So we may recognize this problem as one we did 2 or 3 times in the last set of lecture notes. We're looking for the area between y equals root x and y equals x minus 2, but only in the first quadrant, and bounded as well by the x-axis. And so when we did this before, the problem that we had was that our function, our region, had the same upper bound for the entire region, but it had different lower bounds. But if we think about it in terms of y, no matter which y value I choose that goes through that region, let's say we'll choose this one, the rightmost function, or the one with the larger x value, is always the line. Right? The line's x value is more than the square root function is there. If I looked here, the same thing's true. If I looked at any y value within this region, the x value of the line is always greater than the x value of the square root function. And so we're going to do the same thing that we did to find the area between two regions in the terms of x, but we're just going to do it in terms of y. And because we know that this point up here was the point 4, 2, we're going to integrate from the lowest y value, which is 0, to the highest y value, which is 2. And we're going to do the width of the region here, and the width of that region is just the x value of the line minus the x value of the square root function. But because the thickness of this is dy, we're going to have to go and we're going to have to solve each of these for x, right? X in terms of y. So the lines equation in terms of y is x equals y plus 2. So since that's the larger x value, y plus 2, we'll put that first. We'll subtract the smaller one. Well, here we've got x is equal to y squared. We'll subtract y squared, and that should give us the area of this region. Done a fourth way, right? Different than the other three ways. So as we integrate, we get y squared over 2 plus 2y minus y cubed over 3. We'll evaluate that from 0 to 2, which gives us 2 squared over 2 is 2, and 2 times 2 is 4, and we're going to subtract from that 8/3, and then we plug in 0, that's just a bunch of 0. We end up with 6 minus 8/3. Well, 6 is 18/3, and 18/3 minus 8/3 is just 10/3. And so this is exactly the same answer that we got the last time we did it, but now we can do it in terms of y. So let's do another one here. We're going to find the area of the region enclosed between these two graphs. X equals negative y squared plus 10, which looks like a parabola that has been shifted to the right 10 and opens to the left. And then x equals y minus 2 squared, which is a parabola opening to the right that's been shifted up 2 units. So we're looking for this region right here. And hopefully it's pretty clear why it's going to be good to do this in terms of y. One, the equation's already given to us in terms of y. But two, if I tried to pick an x value in here, like this one, sometimes the upper bound and the lower bound of that region are from the same parabola, which, there are ways to get around that by rewriting that parabola. X positive square root, negative square root. But it's a lot more of a hassle to do that than to just think, oh, well, everywhere I look through here at any y value in my region, one parabola always is the bound of the right part of the region, and the other parabola is always the bound of the left part of the region. So I should be able to just subtract one from the other and integrate from the lowest y value to the highest y value. So our integral is going to end up looking like the rightmost function, which was negative y squared plus 10, minus the leftmost function, which is y minus 2 squared, dy. And we're going to integrate from the intersection point at the bottom to the intersection point at the top. So negative y squared plus 10 equals y minus 2 squared. And y minus 2 squared is going to be y squared minus 4y plus 4. And we'll bring everything to the right-hand side, giving us 2y squared minus 4y minus 6. And as we go through and factor that out, we get 0 equals 2 times y minus 3 times y plus 1, telling us that the upper intersection point is when y is 3, and the lower intersection point is when y is negative 1. So we'll throw those in as our limits of our integral. We'll simplify what's inside of our integral, and then we will solve. So we've got an integral from negative 1 to 3 of negative y squared plus 10 minus y squared. And then if we distribute the y minus 2 out, that gives us a minus 4y, but there's a minus in front, so that'll be a plus 4y. And then the plus 4 that we get when we distribute out ends up with a minus 4 because of the negative in front of it. And we'll combine all our like terms. Negative 1 to 3 of negative 2y squared plus 4y plus 6 dy. We'll just kind of go over here. That's negative 2/3 y cubed plus 2y squared plus 6y. And we'll evaluate that from negative 1 to 3, which is going to give us, let's see here. If we plug in 3, that ends up being negative 18, and then plus 54, and then plus 18. I don't know why we put a 2y cubed here. That's a 2y squared. I'm gonna go back and fix that. And when we integrate 4y, we got 2y squared, which does not make that 54. 2y squared, if we're plugging in 3, that's going to be plus 18. And then we're going to subtract from that the values at -1, which will be a positive 2/3, a positive 2, and a negative 6. So negative 18 plus 18 is 0. Got another 18 there. And then we're going to subtract. It'd be 2 minus 6. So we got 18 minus -4, which would be 22. So we've got 22 minus 2/3. That'd be 66/3 minus 2/3, which would be 64. So we'll do just one more of these. We're going to look for the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. So our first step is just going to be to sketch them and see what this region looks like. So there's basic graph of y equals x cubed, and then x equals y squared minus 2 ought to be a right-facing parabola that's been shifted to the left 2. So the region we're talking about here is this region between the two graphs. And we have to think then, do we want to do this in terms of x, or do we want to do this in terms of y? And the reason we don't want to do it in terms of x is because there are some x values within this region where the upper bound and the lower bound are that parabola, which means when we solve, we got to deal with a positive and a negative square root, and it becomes a bit of a hassle. But for every y value going through this region, the rightmost function is always the cubic, and the leftmost function is always the parabola. So we're going to do this in terms of y, which means we'll need to solve for x, or solve for x in this, x equals y to the 1/3. And we'll do the rightmost function, y to the 1/3, minus the leftmost function, y squared minus 2 dy. And we'll just integrate that from the lower intersection point to the upper intersection point. And in order to do that, we're going to have to take out our graphing calculator here. So let's open up our graphing calculator. And we'll start by graphing. So we can't plug things in terms of x, or in terms of y, we'll just say x to the 1/3 power for the first function. And for the second function, we'll just put in x squared minus 2, and we'll graph both of those. And the x values at which we are intersecting here should be the y values at which we intersect for the other equation, because we have everything in terms of y. And so if we go in and calculate those intersection points by using the intersect function, we can see that the first one over here comes out real nicely. The first one is just -1, so that would be an easy one to remember. But our second one, if we go over here, is going to be a little bit of a decimal value here. And we're going to end up with 1.7930037. So our integral is going to go from -1 to positive 1.7930037. And now we'll just go in and use our graphing calculator to integrate that. So we can real easily if we want to, actually, when we hit math in option 9. And we're going to integrate, as we said, from -1 to 1. We can use this nice little trick that we're doing the rightmost function minus the leftmost function. And so our rightmost function was listed as y1, and our leftmost function was listed as y2 in here. And so what we can do is within our integral, we can actually just copy those values and not have to retype them. We can hit this VARS button. If we go over to the second column and choose option 1, y1 is just going to go in there. And then we'll subtract. We'll do the same thing, VARS, y, VARS. Then option 2. And then we'll just hit dx. And I put -1 to 1 for some reason instead of -1 to 1 point, that long decimal, which is why we've got the wrong value there. So 1 point, I believe it was 7930037. And now we should get the right value, 4.214939673. That is our answer. And that's how we look for areas between curves and areas between the curve and the y-axis, all done in terms of y. Next time, we're going to do a little intro to looking at some piecewise functions that have been drawn in the coordinate plane. That's going to get us prepped for what I call the graph FRQs on page. That's all for today.